Hi, the title of this presentation is Performance Study of Multi-Tenant Cloud FPGAs. I am Joel Mandebi. I would like to acknowledge the contribution of Sujan, my lab mate, and the supervision of my PhD advisor, Professor Bobda. In recent years, we've seen an increasing adoption of FPGA technology in cloud-based systems. For instance, we see here a bunch of companies that are in one way or the other uh, using FPGAs in their portfolio. For instance, Amazon recently released virtual instances that are accelerated with FPGAs. On the other hand, Planify run design space exploration techniques in the cloud to achieve timing closure and reduce design iterations. Our work mostly focuses on virtual instances that are accelerated with FPGA technology. Now, when we look at the global cloud, the global market and the cloud providers that are actually provisioning FPGAs, we observe that most of the deployment are still single tenant, and that can come with resource inefficiency because the FPGAs are not necessarily fully utilized by the cloud users. On the other hand, this may not be the most effective cost solution. For instance, when we look at four of the major cloud providers that are currently using FPGAs, we quickly observe that most of the deployment, not even all the deployment that actually attach FPGA to virtual machines are significantly more expensive for the cloud users than the similar virtual instances of virtual machines that do not provision access to FPGA resources. We are also aware that provisioning multi-tenant FPGAs in the spatial domain comes with several challenges in the domain of security, design flow, and debugging technique. But this is not the purpose of this work. This work mainly focuses on evaluating the performance that can be achieved with multi-tenant FPGAs, and we will mainly focus on I/O performance. Now, let's quickly take a motivation example here. So we compile and program an AES core on a Vertex Ultrascale 9 Plus device, and we observed that more than 99% of the chip remain unutilized. We tried the same experiment with a larger device, with a larger design, which is a split tenant architecture that we recently published at the FCC in 2021. And even though that design is way larger than the AES core, we still see that more than 60% of the chip is still not utilized. Now, this is a rising concern, and because now companies such as Xilinx and Intel are now delivering FPGAs that are bigger. For instance, the Xilinx released a Vertex Ultrascale that now achieves 9 million of logic cells. So it may be interesting to explore architecture that will enable FPGA space sharing. But more importantly, in this work, we want to basically evaluate the type of performance drop or performance benefit that can be the result of FPGA space sharing. Now, our first intent was to look at the literature and try to run do some comparison, but we quickly figured out that the results that were reported were very platform specific. They were not consistent. So we eventually decided to go with the platform that we have built in our research group, and we have actually a paper that was published on this work last year at the ASAP conference. So we use this architecture as the test bed to run multiple experiments and extract meaningful numbers that could eventually help the community to better understand the performance benefit and challenges that can arise from space sharing FPGAs between multiple tenants. So a quick overview on that architecture. In this work, we do not specifically go into the detail of the architecture, but we just want to at least provide an overview. So the architecture divides each FPGA into virtual regions or VR, and the VR have what we call a user region, and that user region will host the user design at runtime. And this design will be programmed through partial reconfiguration. Now, another feature of the architecture is that it enables direct communication at the chip level between the virtual regions that are belonging or that belong to the same virtual instance domain. So basically, we will therefore try to assess the performance benefit that can be achieved or the performance challenges that can be observed in this architecture. For that purpose, we developed a piece of software that we call FPGA Management Service, and that service provide input and output queues to the FPGA. And one observation here is that since it is designed at the software level, here we rely on the TCP receive buffer that has a fixed size of about 80,000 bytes. The consequence of that is this may be a source of bottleneck, and that will eventually increase the latency in case the virtual instances are all competing for this buffer. And if the buffer is full, then that may reduce the overall I/O performance, as we will see later on in the presentation. So we started with studying the I/O latency of the FPGA, of the multi-tenant FPGA, when we increase the number of virtual instances thread that are trying to perform round trip, meaning writing to the FPGA registers and reading the result. But to be able to evaluate this result, we needed a baseline. So we started with the baseline on figure A. So the first thing that we did is we assigned an entire FPGA to a single virtual machine, and on 10 different instances, we basically try to read the round trip latency. And we figured out that it will typically take about for 94 microseconds to perform the round trip. Now, if we do the same operation from the host without relying on the FPGA management service, it takes about 94 microseconds. Now, when we scale the number of virtual instances that are competing for the same FPGA, we observe that about 77% of the round trip completed within 1 millisecond, 21% took about 200 milliseconds, and 2% reach 400 milliseconds. The bottom line is that we see a performance drop of about 10 times compared to when we have a single virtual, when we have a virtual instance that is fully owning an entire FPGA device. We also observe that the average wait time increases as the number of virtual instances increase, which was expected since the size of the buffer in the FPGA management service is fixed. Now, the last experiment that we did was to try to evaluate the benefit of enabling the on-chip communication between the different hardware workload of the same virtual machine that are co-hosted on the same device. For that purpose, we increased the size of the overall interconnect up to 80 virtual regions. And here we want to mention that we do not believe that it will be typical to divide the FPGA into 160 regions. I mean, at least in the near future, we don't believe that that will be the case, but we went that high just to see and evaluate the benefit of the on-chip communication. So we consider two scenarios here. In the first one, there's no congestion on the interconnect, and then in the second one, the interconnect is congested. So basically, we measure the time it takes to move a packet from the two most distant virtual regions. And regardless of the scenario in which we are, we observe that there is still a significant performance improvement compared to performing the same operations either from the virtual machine monitor or hypervisor or from the virtual instances. Now we want to end up with a quick example. It's not typical, it's not really part of this work, but we know that there may be questions about why do we want to divide the FPGA into regions, or why do we want to enable communication between the virtual regions. So you remember a few slides ago, we presented a split CNN architecture that was leaving about 60% of the chip unutilized. So now we divide the FPGA into 5 virtual regions. The unassigned region will be used by the interconnect. The PCI block is also already reserved for PCI communication. Now, the split CNN architecture has 3 major components: RPU1, regional processing unit 1, RPU2, and the fully connected layer. So this is the topology that we have. It would have been better to have RPU1 directly close to RPU2. However, the resources that are available on VR2 are not sufficient to host either VR1 or VR2. So we end up with this placement. We have RPU1 on SLR0, RPU2 on SLR1, and we have the fully connected layer or FCL in VR2 here. This is AES, and we also had a cutting edge application running here. So the bottom line is that the communication through the split CNN took just take about 24 clock cycle, which is still faster than doing the same operation from the software. With that, we want to close this presentation, and eventually we'll be able to clarify a little bit more during the workshop. Thank you.